In this video, we're going to move on to section 5.3, and I'm actually going to divide this into 3 videos. In this video, we'll talk about the divergence test. So 5.3a will be the divergence test, and then 5.3b will be the integral test, and then lastly we'll talk about p-series and the p-series test. And these 3 tests for series is what comprises section 5.3. So to motivate this section, right, in section 5.2, what we learned was that we can find the sum of an infinite series, which is an infinite sum, right? A sum of infinitely many things. So we learned how to calculate the sum of infinite series by taking the limit of the sequence of partial sums. So what we did was we took the infinite sum and we made it finite, and we saw what it would equal at different values, and then we took the limit of that. However, sometimes calculating that limit is difficult or impossible, and that's where these other techniques for finding the sum of a series will come in handy. So in this section, section 5.3, we'll go over 3 techniques, which is the divergence test, the integral test, and the p-series test. So the limit of the partial sums is difficult or impossible. There are tests we can use instead to determine if the series will converge or diverge. Right, so in this section, in 5.3, we learn 3 of these tests. And just to make it bite-sized, I'm going to do them all in separate videos, right? So these are the 3 tests right here, the divergence test, the integral test, and the p-series test. So let's start by talking about the divergence test. And the name of the divergence test is important and helps us intuitively remember what the divergence test is. So the divergence test could only be used to show that a series diverges. So it will never ever tell you that a series converges. We just cannot conclude that with the divergence test. So what is the divergence test? So given a series, the sum from 1 to infinity of an, if the limit as n approaches infinity, so I'm going to take that formula out in my series and take the limit of it, and if that equals some constant that's not equal to 0, or if the limit as n approaches infinity of an does not exist, right, so that means that the function is oscillating or something like that, then the series, the sum from 1 to infinity of an diverges, right? And so the important thing to note, right, so is that if the limit as n approaches infinity of an is 0, that does not necessarily imply that the series converges. That the series, right, the sum from 1 to infinity of an converges. If, right, the limit as n approaches infinity of an is equal to 0, then the divergence test is inconclusive. And so you want to use another test if possible. Use another test if possible. So this is why I emphasized this point here at the beginning, right, was that it can only show that a series diverges, and that we know that it diverges if the limit, right, of the formula in your series is not equal to 0, right? Then we get divergence. But if it does equal 0, that does not necessarily mean it converges. So let's do some examples. So for each of the following series, apply the divergence test. Right, so we're going to do A, B, and C. So for A, we have the series from 1 to infinity of n over 3n minus 1. Right, and remember, our an is the formula inside the series. So in this case, our an is equals to n over 3n minus 1. Right, and then we take the limit of that, n over 3n minus 1, and you can do this however way you love to do it, right? You can use L'Hopital's rule, or you can just see like the highest power on the variable, which is n in this case, is the same as is 1 in the numerator and the denominator. When that happens, we just use the coefficients of the variable, right, of the highest power. Right, and then L'Hopital's rule will give us the same thing. If we do the derivative of the top, that would just be 1, and if we do the derivative of the denominator, that would just be 1. Right, we can also say like, okay, if n is going to infinity, then this minus 1 in the denominator really is no longer relevant, right, when we're talking about this n, this 3n, right, where the n is going to infinity. That minus 1 is irrelevant in magnitude. Right, so if we do the limit of that, right, then we can see the n and the n divide out, and we're left with 1/3. So there's many ways. You choose your favorite way to do limits. Maybe you need to review that from Calculus 1. So then, since the limit as n approaches infinity of n over 3n minus 1 is equals to 1/3, right, which is not 0, we said that the divergence test says that if it's equal to a constant that's not 0, then the series diverges, right? So in this case, we get to conclude that the divergence test says that the sum from 1 to infinity of n over 3n minus 1 diverges. Okay, now let's move on to part B, which is the sum from 1 to infinity of 1 over n cubed, right? So again, our formula an here is 1 over n cubed, and if we do the limit of that, we know dividing 1 by a huge number, that's gonna go to 0. So since the limit as n approaches infinity of 1 over n cubed is 0, then the divergence test, remember, if it's equal to 0, it's inconclusive. And then let's do one more. Right, we get the sum from 1 to infinity of e to the 1 over n squared. Right, and so our an here is e to the 1 over n squared. And if we do the limit of that, we see that the exponent is going to 0, right? That's going to be e to the 0, because 1 divided by a huge number is 0. So then e to the 0, anything to the 0 power, is just 1, right? So then since the limit of our an, which was e to the 1 over n squared, is equal to 1, which is not 0, then the divergence test tells us this series is going to diverge. Says that the sum from 1 to infinity of e to the 1 over n squared diverges. And I'll stop there in this video, and then in the next video we'll pick up with the integral test. Thank you.